We are delighted to welcome the speaker of today's Excite Academy webinar, Dr. David Wallis. He's an associate professor in the Department of Earth Sciences at the University of Cambridge. And Dr. Wallis is a UK RI Future Leaders Fellow, and he heads the Microgeodynamis group, which investigates how rocks deform from the atomic scale of crystal lattices to the scale of the tectonic plates, which is, of course, quite a scale difference, which is great. So his team develops advanced microanalytical techniques, such as HR-EBSD, which we're going to talk about today, to quantify stress and deformation processes in minerals, linking these microscopic observations to large-scale geodynamic behavior. Now, before joining Cambridge in 2020, Dr. Wallis held positions at the Utrecht University and University of Oxford, following his PhD at the University of Leeds on the microgeodynamics of the Karakoram fault zone in the Himalaya. His research has been published in leading journals, including Nature Geoscience, Nature Communications, and Science Advances, addressing fundamental questions about rock rheology, fault mechanics, and the physical processes that shape our planet's crust and mantle. So I'm very happy to have David with us today. So David, the floor is yours.
Okay. So the introduction. Let's just get this up. Is that okay? You can see that okay?
Yeah, I can see it.
Great.
Great.
Brilliant. Yeah, so I'm going to spend the next few minutes talking about this technique of high angular resolution electron backscatter diffraction. I should start off with some acknowledgements. There's several different flavors of this technique these days, but the one that I'm going to describe, and a lot of the groundwork was developed by Angus Wilkinson at Oxford and Ben Britton, who's now at UBC. And a lot of the work that I've done adapting it for geological materials was with Lars Hansen, who's at the University of Minnesota. So let's just get this going. So my aim for the next few minutes is really to give a bit of an overview of this technique. It's a HR-EBSD, it's an extension of normal EBSD that allows you to extract more higher resolution and deeper characterization of the microstructures of deformed rocks. And in particular, the main benefits that it brings are being able to map the densities, spatial densities of geometrically necessary dislocations. So these are defects in the crystal structure, and also to reveal the presence of residual stresses. So these are stresses that are trapped in the crystals whilst they're sitting in your microscope and you're doing your EBSD. So many people will be familiar with what we might call conventional EBSD, where we're using a scanning electron microscope and collecting a grid of diffraction patterns and using them to index which crystal phase we're looking at, and in particular measure the orientations of the crystals, which we could plot up on these pole figures. And we can start to get some information on the internal deformation of the crystals. So we might look at the axes of curvature of the crystal lattice, for example. This is a widely used technique. Many people will be familiar with it. The way that we ordinarily get these data is taking one of these diffraction patterns, putting it through a Huff transform so that the bands in the diffraction pattern become little spots in Huff space. We can find those spots, index the bands, and match the diffraction pattern to a database of crystal structures to figure out which mineral it is and what the orientation of the crystal is. So this is a standard technique that's been going on since the mid-1990s, and we're going to have a look today at how we can go beyond this. Some of the reasons that we need to go beyond it are that this approach to normal EBSD, if we're looking at curvature and distortion of the crystal, there's a limit to the precision of the misorientation angles. There should be angles rather than axes. So it can only measure curvature down to around 0.1 degrees. And a lot of interesting stuff is more subtle than that. For these very small misorientations, normal EBSD is quite bad at recovering the misorientation axis, so the axis of curvature of the crystal. And normal EBSD doesn't measure elastic strain at all. The distortion of the diffraction pattern is just too subtle to show up with this Huff-based indexing technique. So these are all points that we can try and improve on with HR-EBSD. The upshot of that, where we're trying to get to, is to reveal all sorts of new levels of detail in the microstructures of deformed rocks. So here's some HR-EBSD results from deformed olivine, and the types of data that we want to try and end up with are things like this map on the left is a map of the spatial density of geometrically necessary dislocations. So this is where are these defects in the crystal structure, and you can see there's all sorts of, the black lines are grain boundaries, but all the grayscale is showing you all sorts of details of where the crystal is curved and where there are these defects in the crystal structure. The map on the right is a map of residual stress. So this is coming from the elastic strain that's trapped in the crystal, and then calculating what are the magnitudes of stresses that are stored in the crystal. And these are really, a lot of the time, these are really enormous stresses, a really surprising level of strain that the crystals are under. Okay, so that's what we want to get to. How do we do that? Well, the important point to note is that there's much more information in these diffraction patterns if we can analyze them more thoroughly than we would with a normal EBSD approach. And you can imagine, well, here's a bunch of diffraction patterns with green arrows shown as indications, and these ones with blue boxes are showing how the diffraction pattern would be distorted if the crystal is under some elastic strain. So up here, if it's being stretched horizontally, then obviously features in the diffraction pattern are going to be stretched accordingly. If the crystal is rotated between one point and another, then the diffraction pattern itself will obviously also spin around. The point here is that particularly for the elastic strains, the distortions of the diffraction pattern can be extremely tiny. So it might be stretching by only a fraction of a pixel. So for HR-EBSD, what we need to do is measure these distortions with a really sensitive measurement approach. And the way that we do that is to take an EBSD map, pick one point in the microstructure that's going to be a reference pattern. So there's a reference pattern in the background. We can take little areas within that pattern, call them regions of interest. And there's 100 here shown with boxes, and they're all overlapping. And then we're going to compare that reference pattern to a diffraction pattern from somewhere else and try and map out how each of these little regions of interest has shifted around as you go from the reference pattern to the test pattern. So here you can see some of these shifts. These are very exaggerated, and these can often be at the level of individual pixels or even sub-pixel distortions. So in practice, the way we do that is take the reference pattern, take our test pattern, take one of these regions of interest. Here it is. We can filter it in Fourier space to get rid of some of the noise. And then the key step is doing a cross-correlation between these two regions of interest. That gives us a cross-correlation function, and the position of the peak in that function tells us how that little box within the pattern has shifted as you go from the reference to the test pattern. And so we're mapping out the shifts in all these boxes. We can describe those shifts as vectors, and we can fit a tensor to describe those shifts. And the key thing is that the symmetric part of that tensor tells us the elastic strain of the crystal, and the anti-symmetric part tells us how the crystal is rotated as we go from one place in the microstructure to another. And if we use Hooke's law, we can convert these strains to stresses. And if we use the Nye tensor, we can convert these rotations to the densities of geometrically necessary dislocations. So that's a bit mathsy, but the upshot in terms of the data that we get looks something like this. So here's an EBSD map. This is of a little nano indent that we've made in a crystal of olivine. And this is the normal EBSD data and the HR-EBSD data. And we can take a line profile along the top here. And we're looking here at the misorientation, so the angular difference as you go from pixel to pixel. So how the crystal is curved. The key thing here is that away from the indent, this is a perfectly pristine crystal, so there should be no curvature as we go along the top of this map. So that means that the data that we get basically telling us the noise level of the measurement. So down here, we've got that profile along the top, and the pixel to pixel misorientation angles from the normal EBSD data are on the order of 0.1 degrees. And if we do this HR reprocessing, then we get this red data where the noise level now is down at around 1/100th of a degree. So these are really precise measurements of how the crystal is curved. If we go and take a profile right across the indent itself where the crystal actually is curved, then we can see here's the curvature measured with normal EBSD. And then, of course, the HR-EBSD data resolves the nature of that curvature much more precisely. So that's what we're trying to achieve. This is just looking at the misorientation angles, so how the crystal is rotated as you go from point to point, or by how much. The other thing we can look at is the misorientation axes. So that's saying which crystallographic direction is the crystal curved around. This is a little test data set, it's quite old now, from Angus Wilkinson. And this is for quite a small misorientation, very subtle curvature of the crystal. And all these grey crosses in the background are the misorientation axes calculated from conventional EBSD. And the point here is they're scattered all over the place. So although we can measure that the crystal is curved, we can't measure which direction it's curved around. If we take the HR data, do this cross-correlation based post-processing, then we can recover much more consistent, precise misorientation axes. So the upshot of that is with the HR-EBSD processing, we can measure much more subtle curvatures of the crystal, and we can also determine the sense of the curvature much more precisely. As a consequence, we can get better estimates of the types of dislocations stored in the crystal. I'm not going to go through this in detail, but just to say, if the crystal is curved, we can measure the curvature that's produced and capture it in the Nye tensor here. The different elements of this tensor correspond to densities of dislocations with different Burgers vectors and line directions, so different types of defect in the crystal. And we can set this up as a linear algebra problem where we measure the curvature of the crystal, we know the potential types of dislocation that could be in there, and then we have to solve this for the density of each dislocation type. And this whole process works much better if you have these more sensitive measurements of the curvature in the first place from HR-EBSD. What does that look like? Well, these are data from a single crystal of olivine that's been deformed, and each map is for a different type of dislocation in the crystal. And you can see the data from normal EBSD are very noisy, they've got a lot of fuzz in these maps. If we go to the HR-EBSD data, the maps are much cleaner because the data is more sensitive, and the types of dislocation that show up are different between the two data sets. And that's because the misorientation axes are better resolved. So you can get, with normal EBSD, you can get results that look correct, and you wouldn't know that they're wrong until you go and do the HR-EBSD post-processing. The other thing we can get are measurements of the elastic strain. And just to put this in context, this is a plot of strain sensitivity against spatial resolution. And HR-EBSD sits right down in this sweet spot at the bottom corner where we have a good combination of both strain sensitivity and high spatial resolution compared to most other commonly used techniques. Going back to our nano indent, this is a good example because we can pick a reference point far away from the indent where we know the crystal is unstrained, because all the strains we measure are going to be relative to the strain state at that reference point. So we can go and measure the elastic strains and then convert them into the stresses that are trapped in the crystal. And here that's where we've poked into it to make this indent, and the whole crystal is flexed and stressed around the indent. In this case, these are really large stresses on the order of a gigapascal, and you can't measure this at all with normal EBSD. For those of you that get into this, there's a subtlety that when the crystal is very curved and it has big rotations, those rotations can make it difficult to measure the very small distortions that come from the elastic strains. So what we do then is do a two-step cross-correlation process where you back-correct the rotations using a first pass of cross-correlation, and then measure the elastic strains during the second pass. And that gets rid of a lot of erroneous measurement of the elastic strains. We won't go into detail on that, but just to flag that that can be an important part of the analysis. In terms of actually doing the measurement, you have to, a key step is having to calibrate your particular SEM for how the diffraction patterns move around on the detector just from scanning the beam across the sample. So this is quite a precise little bit of work and something that you have to do that you wouldn't normally have to do for ordinary EBSD. So again, just to flag that that's a key step. The other things that you need to worry about, you need to do your microscope calibration on an undeformed standard, often a single crystal of silicon or something like that. During the acquisition, there are additional steps in determining the pattern center as precisely as possible, choosing an appropriate map size. In practice, it usually has to be less than about 200 microns. Otherwise, this calibration that we do isn't precise enough. You need really high quality diffraction patterns because we're actually working with the images of the diffraction patterns. So the data acquisition is a lot slower than normal EBSD. And you also need to store the diffraction patterns so you can work on them afterwards. So this can generate very large data sets. We have a variety of software to choose from, some of which is proprietary, some of which is freeware. So I'll leave them there so people can browse at their leisure. And then in terms of setting it up, you have to choose your processing parameters and choose your reference points. And there are some considerations we could chat about how to do that. And then you get into the task of the data interpretation. A lot of the work I've done, a lot of which is published and out there, is on high temperature deformation. That's one really important use for HR-EBSD. But there is a whole sort of emerging field of applying this technique to metamorphic and igneous rocks, where we might be measuring deformation that's imparted due to changes in pressure or temperature, or reaction processes and crystallisation. Here, for example, Olli Plumper was mapping deformation in calcite that's induced by the growth of this brucite, which expands a lot as it grows. Also in sedimentary contexts, you can imagine using HR-EBSD to analyse compaction mechanisms or diagenetic mineralisation and things like this. So just to wrap up with a couple of examples from these sort of other contexts, this is an HR-EBSD map around, this is again in an olivine grain, but this is around a spinel inclusion. This has come up in a volcanic eruption in Iceland. So as it's been brought to the surface, the spinel is trying to expand faster than the olivine is. And so it induces all these stresses around the inclusion. We can try and model these with finite element models. We get similar distribution of stresses, but the ones that we measure are actually smaller in magnitude. Part of the reason for that might be that there's been plastic deformation around the inclusion, and we can see that in the map of the defects that cause that deformation, the dislocations. So if you're interested, for example, in how these inclusions record processes in the magmatic system, it might be useful to know how this little capsule has been modified during its ascent to the surface. And last example, rather than looking at the sort of deep ductile deformation in the mantle, for example, Giovanni Toffel has done some recent work on looking at brittle deformation in the upper crust, well, sort of mid-crust, and he made a series of HR-EBSD maps in this garnet. This is a pseudo-tachyllite, which records as a fossilized earthquake frictional melt. this garnet next to it is all pulverized by the seismic shock during the earthquake. And so Giovanni went and made maps going from far away from the earthquake to right next to the earthquake and measured out how the stresses trapped in the crystal increase as you go towards the fault, how the defects in the crystal become more abundant as you go towards the fault plane, and what these mean for the energy budget of the earthquake and how much energy was available for producing heat and to be radiated as seismic waves. So there's all these different contexts in which mapping the deformation of the crystal can be really useful. So that's quite a quick romp through all the different aspects, but just to summarize, HR-EBSD gives us this really good angular resolution to map how the crystal is distorted, can map the sense of that distortion much better, and these both improve estimates of the types of dislocation trapped in the crystal. We can also map elastic strain and hence residual stress very precisely, and this is something you can't do at all with normal EBSD. So I'll stop there, and I'm very happy to take any questions.
David, for this really brilliant overview of all kinds of examples, which I found very exemplary. So please pose your questions in either the chat or the Q&A, and otherwise raise your hand and I will give you the floor. But in meanwhile, so what are the main limitations or challenges when applying this technique to geological samples? Are there any, or is it really straightforward?
Yeah, no, there's definitely a lot of things we need to think about. One of the most practical ones is you need a really good surface polish on the sample, much better than even for normal EBSD. So this technique's so sensitive that if you have any remaining really subtle scratches in the surface, they really stand out like a sore thumb in the results. So you need to put really careful thought into how to polish and prepare the sample surface very cleanly. Another thing in terms of data acquisition is the technique only really works well up to map areas of a couple of hundred microns. And so with normal EBSD, you can map areas of a centimetre or more. So this is really quite limited spatial extent. So you have to choose your map location and how you're going to sample the microstructure needs quite careful thought. So it can reveal a lot of detail, but it needs quite careful preparation to generate the results that you might be looking for.
Right. So when you say you need a lot of polishing of the surface, right? So is there also maybe then some challenge to also prepare the samples, and then you really have to make sure that you are looking at the crystal? Or I can imagine that some samples it's very difficult to distinguish some, what's the crystal and what's the environmental other stuff clinging to it, as I
yeah you're absolutely right. Yeah, one of the things that helps with this is on the EBSD detector there are additional detectors. There's little diodes that can show the 4 scattered electron diodes, and they give you a complementary image of the sample, and they're really good at showing up the scratches. So if you crank up the contrast on these other detectors, you can try and make sure you're not looking at scratches and getting artifacts, and you're really looking at the deformed crystal.
Right. Okay. So you have ways of kind of looking at that and making sure that you are looking at the right thing.
Yeah.
Okay, great. So I have a question from Andre Niemeyer. Please ask your question. I think you were, yeah. Please go
Hey,
ahead.
David, how's it going? Nice to see you
Hey,
again.
okay.
You showed some maps with very nice examples. They're all relatively big range. You mentioned the 200 micron sort of limit in that direction. How about very fine grains? You know where I'm coming from. So what's the limit on the other direction?
I think it depends a lot on the material. So for silicates and carbonates and stuff, if you go too small, you get limited by beam damage. So once you've mapped one row of the map, there'll be some damage underneath it and you start mapping into your own damage. I think things like quartz and calcite, it's difficult to go below about 0.5 micron. Yeah. So I guess you're thinking more nanoscale.
Perhaps, yeah. What's the lowest grain size you've tried successfully?
We've mapped things that are like 1 micron,
Okay.
which would be, but that would be like forsterite or something, which doesn't damage as much. On metals, people have definitely done like a few hundred nanometers, because you can go down to a step size that's like 50 nanometers or something. It depends a lot on the material. Yeah.
All right, thanks.
Thank you for your question. So there's another one. So how about mapping deformations in pargasites and apatites?
And what was the first one? Pargasite.
Pargasites. Pargasite.
Yeah, that should work okay. Yeah, both of those I think would work okay. We've done some work on other amphiboles. The monoclinic symmetry makes it a little more complicated to think about how you set up. If you want to go from the rotations to the GND densities, the maths gets a little more complicated. But in principle, collecting the rotation and strain data on both of those is eminently possible. Yeah.
So for me, what are these kind of materials? What is it's a rock sort of some sort? Or?
Yeah, so we're talking about different minerals within the rock.
Right,
they all have some of them diffract better than others, some of them polish better than others, some of them damage under the electron beam more than others. Yeah, generally speaking, the technique is quite broadly applicable.
Yeah. So how do you account for the kind of like to make sure that you're not comparing apples with pears, or is it just not you can't use it as such to compare those two minerals, or?
I would say it's tricky to think about comparing between the minerals, but you can also refer to external benchmarks. So there's a lot of cool work from X-ray diffraction, which usually involves synchrotron X-ray diffraction to get high spatial resolution. So when we first started doing HR-EBSD, people were a bit suspicious of how big the stresses were that we're measuring. But there's been a lot of cool work from X-ray diffraction as well recently, which shows exactly the same thing. So with X-ray diffraction, you don't have the same spatial resolution, but it's a more established technique, so people are very confident in the results. And HR-EBSD compares well against those sort of benchmarks.
All right, nice. So I've got a question here. What polishing range or level is required for HR-EBSD thin sections?
Yeah, so you would, for a thin section, you just polish it like normal with diamond, typically with diamond grit down to say 1/4 micron, and then either colloidal silica or nanocrystalline diamond. But the trick here is you really need all the polishing equipment to be super clean to begin with. So I'll be like ultrasonicking everything, the holders, the polishing cloths, typically using fresh polishing cloth each time if I can. Because you can imagine just one little tiny little bit of grit that would normally not cause any problems for normal EBSD. If it drags a scratch across the sample surface, that's going to have a huge amount of elastic strain all the way around the scratch, and it will really mess up the results. You can also do ion beam polishing. Only covers a smaller area, so you wouldn't be able to do a whole thin section with it, but you can either do cross-sectional or sort of surface ion beam polishing for particular materials. It also is much easier on single phase samples than polyphase samples, because if you have a little bit of a harder mineral like garnet, if it breaks out of the thin section and starts rolling around as you're polishing, that's going to mess things up as well. So it depends a lot on the sample, but in principle, it's the same as normal, but just done extremely carefully.
Right. And so is it also something that you provide, being in the Excite network and being able, just imagine that I'm a scientist who would like to use HR-EBSD in your lab. Is it also something that you can help me with the, these kind of tricks tips
Yeah,
and
that's a great
tricks
question.
for
Yeah,
getting
yeah.
a
So
nice polishing result?
yeah, we can do that. We sometimes have had users either send the sample ahead of time so we can have a little look at it beforehand and try and improve it if needed, or I sometimes ask users to add on an extra day or two so they can do some of the preparation work when they arrive before the analyses. Yeah.
Great. So I've got one last question. So how do you see the technique evolving over the next few years?
I think
About that.
yeah, I think the main sort of direction is going to be seeing applications to a wider range of problems. So we've been doing a lot of work on you know, high temperature deformation, which is an obvious thing to work on, but really like we're only just starting to work on applications to stresses induced by metamorphic reactions. We're finding distortions in igneous crystals that you can't see with any other technique, and they tell you something about how the crystal grows. Compaction and deformation of sedimentary rocks, as I mentioned. So there's a whole range of avenues that we can apply the technique to that we've barely begun to explore. There's also, more generally for HR-EBSD, I've presented sort of the traditional way of doing HR-EBSD, where you get these little sub-regions within the pattern. But there's people who are exploring new ways where you fit the distortion of the whole diffraction pattern at once, which has some pros and cons, or using simulated patterns as a reference rather than using a different pattern from within the sample. And again, that has pros and cons. So there's different directions that the technique is going in, but at the same time, we've already got this sort of established methodology that works very nicely, and there's a whole range of different directions that we can try and take it in to apply it to different geological problems.
So you're only just starting, as I understand it.
Yeah, that's right.
Great. Well, I think that's a great conclusion. And thank you very much, David, for being our speaker today at the Excite Academy webinar. And I hope you enjoyed this webinar. Hope to see you again next time. Next month, we have an Excite user talking about her experiences using the facilities within the Excite network. So yeah, if you are looking to use HR-EBSD, the call is still open, so you can actually be in David's lab and work with David himself. I presume, if you want, you can apply for free of charge access. So with that, I will leave you. Thank you very much and have a great day.